the 3D printers.
Okay, guys, we're going to go ahead and get started. Welcome to the IoT meetup and welcome to the Nest. The Nest is actually led and ran and managed by Andrew Newey, so thank you, Andrew, for letting us stay here tonight and hold the IoT meetup. He's also co-host. And it's also my pleasure to introduce Dr. Arman Sabbaghi, who is the CEO of Aragev, if I pronounced everything correctly.
That's exactly right, yeah.
Okay, good. And he also purchased the pizza and the refreshments. So, you want to go around the room and have everybody introduce? I think that's great. Well, let the speaker first introduce himself.
Yeah, so Arman Sabbaghi, CEO and President of Araqev. We created Aragev in April 2020, and our software uses our patented machine learning algorithms to solve the $2 billion problem in quality control for 3D printing, and I'll be sure to tell more about that later on. I would like to note we have some samples of our 3D printing products from Markforged Metal X, so please feel free to take a look at it, touch it if you like. It'd be great.
And my name is Shannon Dubendak. I lead the IoT Peoria meetup. Actually had a 25-year career at Caterpillar and currently work at T-Mobile in the manufacturing vertical. So if anybody wants to talk about cellular solutions, asset tracking, and so forth, I would be happy to talk to you about that.
My name is Jack Patterson. I'm a mechanical engineering student at Bradley. Taking a little machine learning course now, as well as I've been doing tons of 3D printing.
I'm Ryan Brady. I'm a maintenance tech at Caterpillar, and in my free time, I like to build 3D printers.
Cool.
Hi, I'm Ruben Cummings. I'm president and founder of a data consulting company based out of the Nest here called Aragev. And just happy to see how you guys integrate AI and 3D printing.
I'm Kayla Miller, and I do custom jewelry design using CAD and potentially the 3D printing process.
I'm William Staples. You can call me Will. I'm the owner of Human Innovations LLC. And hopefully, nice to meet you all and connect with all of you.
My name is Brett Nelson. I work for Human Innovations LLC, and the biggest thing I do there is I support all of our incoming resin models to make sure that they succeed in the highest quality that we can produce.
Paul Fry. I was an engineer for the State of Illinois Department of Natural Resources for 27 years and hosting at my house Will Staples and Brett here to have their business there.
I'm Z. Colmus. I just finished up at Illinois Wesleyan with a computer science major with a focus in data science, and I'm just really intrigued in all sorts of applications of machine learning and AI.
I'm Jane Talkington. I was just hungry. Actually, I work at the Turner School of Entrepreneurship and Innovation, and we host student competitions and do a lot of co-curricular activities. Great.
I'm Nate Dominic, the director of G-Beta Distillery Labs, early stage startup accelerator right here in Peoria. So, nice to see you.
Say it right. Dominique.
Oh, Dominic Guini, yes.
Remember it, we say it right.
I'm John Ingalls, co-founder of Smiley Graphics Studio with my wife, Dee, who is the eco-friendly package designer, and I do web development.
I'm John LaHood. We've got a 3D printing startup here in Peoria. We're using Additive Manufacturing to produce color cosmetics.
I'm Caroline LaHood with Color Forge, always just trying to keep up with John on the additive manufacturing side, so hoping to learn a lot today.
I'm Aaron Gigas. I work for OSF Innovation and have the pleasure of helping Distillery Labs get up and running. So I work with Nate and Andrew with all the great things and collaborate with Shannon and others for great meetups like this.
I'm Bailey Lashina with Streamline Architects. I'm a project manager, and I work here at the Nest on Fridays.
I'm Andrew. I work at the Nest too, and I run the Nest. I'm so pleased to have Arman here from Indianapolis, so thank you for coming.
Thank you.
That's awesome. One last comment I just want to make. If you have not joined the IoT Peoria meetup, please do. It's meetup.com. Look for IoT Peoria and just join the group. They'll be happy there. That way you get messages and stuff when we come to events.
All right, excellent. So, as I mentioned before, we work on the problem of quality control in 3D printing, and we're using our machine learning algorithms to learn quickly from all printed products how to improve accuracy. And improve accuracy for different types of shapes that you're working with, different types of materials, and even different types of processes. By means of machine learning, we could reduce reprints by 70% and triple throughput. So I've been working on 3D printing for a decade now, ever since I was a PhD student in 2012. And I'll distinctly remember when I was a PhD student just how revolutionary I found to be 3D printing. You know, the idea is pretty straightforward. You have a computer-aided design model, you feed into your machine, and it prints it out. It has a lot of advantages compared to more traditional subtractive manufacturing paradigms. But ever since I started working on it in 2012, up to this day, there's always been this problem of quality control with 3D printing. And this problem exists across a whole host of different types of additive manufacturing paradigms. The first 3D printing process that I've worked with in which this problem existed was the stereolithography process. The Ultra machine that was manufactured by Envision-Tech, which has been acquired by Desktop Metal recently. This is a pretty, really cool manufacturing technology. The idea is you have a bucket of liquid resin inside the machine. You input in your CAD model or your STL file, what have you, into the machine, and this very intense light source shines down on that bucket of liquid resin to solidify layer by layer your product and build it up additively. You know, going back to 2012, this seemed just complete science fiction, but it actually works out very nicely. It has a lot of advantages in that you could potentially save materials and build really cool products in a very straightforward way. But a big disadvantage is that you have this rapid heating and cooling cycle going on inside the machine, and that introduces some shape shrinkage or warpage. So you may want the boundary of your product to be as circular as possible, but when you take it out of the machine, you'll see that it's actually kind of shrunken and it doesn't meet specs. So that's a big problem. In stereolithography, that problem exists. That problem also exists for other laser-based additive manufacturing machines. I've also had the opportunity to analyze data and work with data from the EOS M290 machine and the Renishaw AM400. And for these two types of machines, the idea is, again, you feed in your CAD model for the product that you want to build out, and you have a bed of metal powder inside the machine. And there's this intense laser that shines down on that bed of metal powder and solidifies it to build up your product, again, additively. This is great for critical applications. Think about aerospace, national defense, in which you no longer have to create 30 distinct products that then you put together to build a jet engine, but maybe you print out 4 products in this machine that are very organic. They enable you to use less fuel, and they're just better in terms of other properties as well. But you still have the same kind of quality control issue because, again, you have this rapid heating and cooling going on inside the machine, and that introduces shape deviations and distortions. That could be critical for those end-use applications. If you're flying at an airplane that has G additives, additively manufactured products inside the jet engine, you want to be sure that they meet spec. Otherwise, that could increase the probability of critical failure, which could be disastrous. Most recently, and these products specifically, we worked with the Metal X printer from Markforged, and this is also a very nice additive manufacturing technology in which you extrude metal powder that's kind of encapsulated in a polymer type of material to build up your product additively, and then you wash away the polymer, you put it in an oven, sinter it, and you get your final printed product. We have here 10 products that were manufactured using the cheapest type of stainless steel for the Markforged Metal X. Again, this is a very cool additive manufacturing technology with a lot of advantages. It still has the disadvantages that when you take it out of the oven and you look at it, the dimensions don't meet spec. It doesn't have the right type of quality. Now, how did people deal with this quality control issue in the past? What they typically did using their existing software is to go through a lot of design iterations until they finally identified how best to print out a product, either how to change the CAD model or the STL file, or how to change the hardware settings for the machine. And it could involve as many as 10 design iterations without any learning from the past. And when you're printing out big products, when you're not learning from the past, that could be quite painful. There does exist some software solutions to try to enable people to learn how to control the quality for their 3D printing products, but they typically involve physics-based models, and those kinds of software do not offer any types of time savings. In fact, the amount of time that it takes to run existing software solutions that are based on physics-based models can be as much as it takes to actually print out a product itself. Literally, it could take you a day to print out this product. It could also take you a day to run those models to understand how to control the quality of your 3D printed products. So ultimately, I could tell you from my own experience just printing out these products how frustrating and how painful it is to think about having to go through a lot of design iterations, waste a lot of material, and spend a lot of money until you get something that meets spec. You know, this product right here, for example, let me just bring this to the camera for everyone to see. This product right here easily costs $100. And if you have to go through 10 design iterations just to understand how best to print out that product, you know, that's just a shame. That's just a waste of materials, a waste of money, and a waste of time. Currently, these losses in terms of the need to perform a lot of design iterations that control quality add up to nearly $2 billion globally. And that number is only going to be increasing as more and more people use 3D printing and as it becomes more commonplace. So there is fundamentally a need for software to exist to enable people to learn from the past so they don't have to do a lot of design iterations, for this software to be run in a very rapid manner so you don't have to spend a day waiting for the software to give you the output. You could get it in seconds. And for you to reduce the number of reprints and get quality in one or at most 2 design iterations. And that's why we created our software solution, a Mappy. A Mappy enables closed-loop smart control in additive manufacturing based on our patented machine learning algorithms. It runs in seconds, and it could literally reduce the number of reprints by 70%, as I mentioned before, triple throughput, by leveraging the rich amount of information that exists in your previously manufactured products, even scrap products, even those that people typically just threw away and thought it was just completely useless. So how does a Mappy work? The basic idea is from your printed products, you scan them to get a point cloud of data that you then feed into the machine learning algorithm. And I'm not going to go into a lot of details about the machine learning algorithm yet. If you have questions, please feel free to ask. All I'm going to say here is that we use neural network algorithms whose inputs are the scanned point cloud data as well as your nominal STL file. And from the machine learning algorithms, we can then understand how to change the STL file in order to improve the manufacturing process. The idea being that we can compensate the STL file so that in the future, when you print out a product, it more accurately meets the specifications that you want. And furthermore, we're leveraging next generation machine learning algorithms, what's called transfer learning. So we could transfer models from previous shapes, previous 3D printers, even previous materials, so that you don't have to start from scratch for every new type of shape, material, or process that you may be working with. And that's really what gives our software solutions a distinctive advantage over existing software solutions. Due to our use of transfer learning, we can easily adapt to different types of materials. For example, we are able to apply our algorithms to transfer models from Ti-64, a titanium alloy, to another stainless steel alloy, 316L stainless steel, for an EOS M290 machine. So we can easily adapt to different types of materials. We're also agnostic to the type of printer that you may be considering. We're not just developing solutions for an EOS or Renishaw or Markforged. We are developing a software solution that can be run on any type of 3D printer that you may be working with. And it's fully automated. We're using our very computationally efficient neural network algorithms that run in a very automatic way and enable you to transfer knowledge across all the different things that you printed in the past to get high quality products. And at the end of the day, again, we could reduce reprints by 70% and triple throughput. We validated our software in over a dozen different types of case studies. I mentioned before that we worked with the stereolithography machine. We've also worked with laser-based additive manufacturing, EOS and M290, Renishaw M400. I'm going to give you a little bit of details about how our software works for the powder extrusion machine, the Markforged Metal X right now. Before I get to that, I just want to say that in our most recent case study for that Metal X printer, we were able to show that we could reduce shape inaccuracies by 30 to 60%, depending on the complexity of the geometry at hand. So let's talk about that specific case study. There are two types of shapes that we're considering for that. One is a very smooth shape, kind of an organic shape, these domes at the top, and then the other is a more complex shape with straight edges and sharp corners, these rectangular prisms at the bottom. And the idea is that we want to show that in 1 or 2 design iterations, we could control the accuracy of the 3D printed products. So what we're going to do is we're first going to start with those simple shapes, the dome shape. And we're going to do 1 iteration with those shapes to show just how much we reduce in accuracy. And I'm going to show in a couple slides that we reduce it by 60% by means of our algorithms. Then what we're going to do is show how we could transfer the knowledge from the dome to the rectangular prism, so as to leverage all the information from all your previously manufactured shapes, so you don't have to start from scratch with a rectangular prism, so as to reduce the number of reprints for that shape as well. To make things kind of more interesting, we purposely printed out products so that in the first design iteration, something changed and you wouldn't achieve the accuracy that is expected because of some kind of lurking change in the hardware. So it required 2 design iterations. And what we show is that we could recover from a failed build. You could leverage that information from what you would previously consider to be a scrap product, put that into the machine learning algorithm, and still identify how best to print out products and converge to a good solution at the end of the day. So let's show just how we improve accuracy. So what I have here are some heat maps for dome inaccuracies. You don't have to worry about the X or Y labels. All I would say is you have to worry about the colors in this heat map. The darker the color, that shows the worst type of inaccuracy. And you can see here we have these 3 domes, small, medium, and large, and they're all pretty dark shapes. But we can leverage this information in our machine learning algorithm, and then in 1 design iteration, when we compensate those domes and print them out, what we could see is that we dramatically reduce the amount of shape deviations in the product. You could see that those dark colors become very light in these compensated domes. And furthermore, just looking at the overall measure of inaccuracy, what we call root square mean of deviation, we reduce it by 60% in the first iteration for those compensated domes. So let's do the prisms now. Here are the 3 original prisms in which we didn't do any compensation at all. And again, I wouldn't worry too much about the X or Y axes. These are just heat maps of shape deviations. What we can see is that there are pretty dark colors in here, which is indicating some severe shape deviations. We purposely set up the validation study so that you wouldn't get a good compensation in iteration 1. We wanted to test if you could recover from a failed build. So in iteration 1 here, what we see is that we still have some pretty dark colors in there in the heat map that we haven't adequately corrected for shape deviations. But that's okay, because we could take these failed builds from iteration 1 and feed them back into our machine learning algorithm to make it a closed loop system. And then in iteration 2, we actually do recover from those failed builds, from those scrap products, which people just typically threw away. We leverage that information and we show you that indeed we can improve the shape accuracy for the printed products. And we improved it by 30%, leveraging our transfer learning algorithms. So we've been just pleasantly surprised as to how consistently our algorithms can improve shape accuracy across a whole host of different types of printers and materials, and this is just one case study that I showed you. We've spoken to a lot of companies about direct partnerships and about applying our algorithms for their systems. Among these companies, we're under NDA with 4 of them, and we're currently actively working with those companies that we're under NDA with to demonstrate the utility of our algorithms for their systems. 2 of them have already given us data from their 3D printing processes, and we're working with them on that. So if there is one thing that I'd like to leave you with today, it's this request. For those of you who have 3D printers or have your own 3D printing companies, I'd like to request that you try our software, Mappy. I'd like to note that there's no need for you to print out new products to try our software. You could use your products that you've printed out in the past, even scrap products, things that you threw away in the trash heap. By all means, don't throw that away, because those products are rich in information. If you scan those products, we can help you understand how best to improve your printing processes going forward in the future to improve the accuracy for new shapes and new materials they want to print out. Furthermore, we could help you evaluate these predictions from our algorithms and get some insights about your specific 3D printing processes that maybe you missed by not leveraging that information in your printed products. And furthermore, if you're willing, we'd be more than happy to talk with you about validating a Mappy for your systems, showing you exactly how much we can improve the shape accuracy for your 3D printing processes so that you can see the utility of machine learning for 3D printing. So to summarize, there's a tremendous opportunity here to make 3D printing smarter by means of machine learning. And I have to say that based on the expertise of the people in my company and working on machine learning for 3D printing for the past decade, we're uniquely positioned to solve this problem and hopefully help move the community forward and usher in that way, a new industrial revolution for 3D printing. So thank you all again for giving me the opportunity to speak here today. I'd be happy to take any questions that you may have.
How do you scan your prints?
Right, so we have two types of scanners that we used in the past. We have a ferro laser arm. I shouldn't say we used. We use a ferro laser arm, which is a kind of a device that kind of looks like a gun, and you position it around your 3D printed product to collect point cloud data on it. So that's one type of scanner. It's fairly accurate in terms of its resolution. It could be kind of hard to move that device around to get a full accurate point cloud data set, but that's one thing you could use. Another thing that we've used is a desktop scanner with a rotating platform. You just put it on a platform, there are sensors located around it, the platform moves and collects data from your product. So those are the two types of scanners that we used in the past. Yes?
So does each client basically have their own model that's been built, or are you sharing the information between sort of all of the sort of iterations of products, or is it kind of just solely focused on like what you have done in the past?
So going forward in the future, what you bring up is exactly what we're trying to do. We're trying to leverage data across all the different models, across all the different materials and 3D printing processes that our customers have used, so that when it comes to a new type of machine or a new material, new shape, we don't have to start from scratch. We can leverage that entire knowledge, that entire database, to understand how best to improve the quality for that 3D printed product. As of this time, we're still under NDA with these companies. We're just starting to work with them, so we haven't done that yet. And there are some significant privacy concerns that we have to address in order to move forward in that regard. But that is the future goal, to have this cloud platform where everyone uploads their models, and we can leverage that data to understand how best to improve the quality for new shapes, new processes, and new materials.
I guess that makes sense with IP and everything.
Indeed. Especially if you're doing critical things like DoD related, national defense related. It's a very tricky subject.
Gotcha.
Did you have a question?
Yeah, so is it just the finished piece that you use to double check, or is it the actual CAD itself that runs through the process first before the 3D print? That's actually double check to make sure that it's
So that brings up
standards.
Yeah. So that's the wonderful thing about the machine learning algorithm that we're proposing. The idea is that since you're leveraging all the information from past builds, when you have a new CAD model or a new STL file, you can simulate, without even printing out that product, what you expect the shape deviations to be. And based on that initial simulation, which you can do, you could then develop a compensation plan or some idea of changing the CAD model so that hopefully you wouldn't observe as much deviation as you simulate. But of course, there's a feedback loop, and this is something that's really critical to the success of our algorithm, that if you print it out and you don't have the right specs that you expect, you could take that data from that failed build and relearn from that. Yeah.
And that will work with any CAD software and any 3D printing software.
So in terms of what we worked with in the past, we worked with these fairly convex solid shapes. If you have an extremely complex shape, I can't promise that at this point in time. That needs further development. But there is definitely some consideration that needs to be taken account to the complexity of the shape, if it needs to connect with other types of shapes, and just the size of the shape as well. So, yeah. Oh, yeah.
So it like modifies like the STL or a 3D model as opposed to like print settings and on the printer specifically? Like, why?
Indeed. So our vision is again to be agnostic to the type of machine, the type of material, those kinds of things. We could easily incorporate print settings, machine-specific settings as additional inputs into the machine learning algorithm. There's nothing stopping us from doing that. But what we're trying to understand is if you wanted to have a solution that works across all machines in which you didn't have to specify those inputs, just how much could you improve the quality for your 3D printing process? And what we've just shown in one case study for the Markforged Metal X, in which the inputs are the nominal STL file as well as the scanned point cloud data from your printed products. For certain types of shapes, those two sets of inputs can easily reduce shape inaccuracies by 30 to 60% in and of themselves. And adding in additional print parameters, machine-specific things, can further reduce shape inaccuracies. But that in and of itself is a pretty good sign that there's a long way that you could go with just those two simple inputs before you become more machine dependent in terms of other inputs. Yeah.
So with the fact that you're modifying potential STL, in some cases STL itself could have a data loss and some inaccuracies when it goes from a CAD to an STL file. So how do you deal with those issues?
Yeah, we haven't come across that issue yet, but that does introduce a very interesting feature in just the quality of the transfer from CAD to STL, as you just mentioned. So there's, as you're doing quality control for 3D printing, there's this entire initial set of pre-processing steps that you need to worry about as well. And again, we haven't come across that issue yet, but I can tell you when it comes to pre-processing, when you're scanning these kinds of products, for example, just the quality of the scan itself can be a significant issue. And you may have to do multiple types of scans until you're satisfied that you have an accurate representation of your 3D printed product. So I'd imagine that as you're going from CAD to STL, you might have to try different types of software and make sure that you identify the right one that in which the STL captures the right representation from your CAD model before you use that as an input into the machine learning algorithm.
How much does your software cost?
So that's open to discussion. Yeah. Exactly.
So,
that's exactly right.
So to build on that, like you say, try the software. How do we do that?
Right. So what I'm doing right now with two companies is they have specific shapes. They provide the data. We run the software on the data. We give them the output in terms of predictions, in terms of an understanding of how to change the STL file, and then they validate it. And then we move from there and have a further discussion about software adoption and payment and those kinds of things. For anyone in this room, I would like to suggest the following plan of action. Try our software for free. Just one set in which we give you some idea about the predictions, we give you some idea about how to change your STL file to get better accurate products. And then if you find that it works well, great, let's have a conversation after that. And if it doesn't work, it's really no loss on your end because these could be scrap products, things that you throw away. We're just saying, let's try to learn from those to see if we can improve your 3D printing process.
So do they send you their, 3D printed parts that you scan, or how does that work? Because not everybody has a scanner.
That's exactly right. So we can talk about that. If you don't have a scanner, we have access to scanners, and so they could ship it to us, and we could talk about that kind of solution as well. Yeah. Yeah.
A little bit more specific about the algorithm. You said you're using neural networks. Like what sort of architecture are you using? You don't have to get too specific if it's, IP, but.
Right. So yeah, I'm not necessarily too worried about that. So when it comes to the architecture, you'd be surprised as to how far a single hidden layer neural network will take you. These days, people are talking about using deep layer neural networks. They think that that's the best solution. But I'm actually quite shocked that if you use a single hidden layer neural network and your hidden weights are chosen in a random way, you're not even optimizing those, you could get a very accurate simulator for your 3D printing process. And furthermore, develop these compensation plans that we've shown can improve the quality for your 3D printed products. So it's nothing too complex. It's extremely computationally efficient because it's just one hidden layer with a lot of the hidden weights chosen completely at random in an informed way, and it still gets the job done.
Gotcha. And do you use sigmoid as your activation function?
Hyperbolic tangent, we've used ReLU in certain situations as well, but hyperbolic tangent seems to work out pretty well. And there's another reason why we want to use neural networks. Just going back to your previous question, I just realized this as well. The neural network architecture is very nice. It really does do a good job of facilitating transfer learning. Because the idea is that when you learn a neural network architecture for one type of shape like this, and when you're working with another type of shape, you don't have to relearn the entire neural network. You could use this neural network as the basis and add on additional hidden neurons that capture unique geometric features for the new shape that you're considering, and in that way kind of build up a hierarchical model so that you could go forward and leverage all the previous data from the past. So I think neural networks, pretty straightforward here. They really do do a good job of facilitating transfer learning, and they're extremely computation efficient. They could run in seconds, not hours, not days.
Can your technology be used to apply to the actual manufacturing printers? In other words, are you correcting just through CAD models, or can your technology actually be applied to the printers themselves to make them more accurate?
At this point in time, we're just working on the CAD models or the STL files, not the actual printers themselves. And again, this kind of corresponds to our current mission, which is to be machine agnostic. If we were to try to apply it to a specific type of printer, we have to be very heavily devoted or dedicated to that printer. And we don't want to necessarily narrow ourselves down too much to a specific type of printer.
So I'm curious about the use cases at the manufacturing companies that you work with. So from the use case perspective, are they trying to do on-demand manufacturing of parts in a production run, or is it like for spare parts, or do they?
So spare parts definitely is very important, especially so we're working with partners at UTRGV, University of Texas Rio Grande Valley, as well as American Bureau of Shipping, in which the idea is that when you're in the armed forces and you need to 3D print a spare part for a critical component or for some kind of critical service, this is where our algorithm can come into play, leveraging all the things that you printed in the past to more accurately print out a product in that critical setting with less reprints and better accurate products at the end of the day. For the companies that we're currently working with, that we're under NDA with, it's not necessarily critical parts, but they are working with very complex geometries, and they want to understand how to reduce reprints in an informed way to get highly accurate products.
How close are we to actually doing on-demand printing, 3D printing in a factory at scale?
I think we're very close. I don't have specific metrics to kind of quantify at this stage. I'm sure that there are people in the audience who could give more informed answers than I may have, but at this point in time, there exists a lot of online services where you could upload your STL or CAD model. They could give you an estimate about how much it will cost to print it out, and they will print it out and ship it to you. They also have consulting services where they work with you to try to understand the design that you want to print out, see if there's a better way of printing it out using 3D printing processes so that you're satisfied with the type of product that you have at the end of the day. Yeah.
So, we're 3D printing homes now. Can your software be used for that in terms of, minimizing any sort of large-scale issues?
Yes, so that's a wonderful thing that we're moving toward going very soon. We've worked with this kind of scale of product, which is fairly moderate in size, or some people would say even small in size. When it comes to 3D printing things as big as a house, there are a lot more complications involved with that, and arguably the shape deviations are even a more significant issue on that large scale compared to the small scale. So that is indeed exactly what we want to move forward going in the future, and show that even for large-scale 3D printing, machine learning can be useful. We haven't gotten data yet for big area additive manufacturing, but that's indeed something that we're very interested in and what we want to target going forward in the future.
Are you limited at all by scanning technology, or does it give you all the information you want?
So scanning technology gives, well, first of all, if you think about it, when you have a shape, you have to have some kind of way to quantify shape inaccuracy. So scanning technology plays a critical role at the end of the day just for quality monitoring. You've got to have it at the end of the day. For these kinds of scales of shapes, Scanning technology is very straightforward to use, and it does a good job in terms of capturing inaccuracies. For large products, going back to the idea of 3D printing a house, scanning technology is a little bit more complicated, but if you do it in a smart way, where you scan different parts of a product separately and stitch them together at the end of the day, you can get something that you can then work with and run in our algorithm to see if you can improve the quality of your 3D printed product.
So the one of the challenges is getting a proper scan, right? Because you were talking about challenges in getting a good scan.
Yep.
Do you foresee that to be a barrier in terms of adoption of software?
Yeah, indeed. So that could indeed be a very significant barrier to the adoption of the software. And I remember talking to an expert in 3D scanning several years back, and he said, when it comes to 3D scanning, we're always 5 years behind in terms of manufacturing capability. So scanning still has a long way to go, especially to make it readily available to anyone who does 3D printing to collect some kind of information about the quality of their builds. That is indeed a big barrier to
And
adoption.
have you considered, ways to address or manage this barrier?
Right. So obviously one way is partnering up with 3D scanning companies, bundling our software with their hardware and selling it as a package to customers who want to do 3D printing. That's something that we've considered in the past. We haven't yet done that, but that's indeed something that is part of our future plans.
So you're raising your hand. Very common. Is anybody online? Anybody wants to come off mute and ask some questions or type in questions? We'll look for those as well.
Let's see. Anybody? I don't see anyone. Okay.
Any other questions in the room? Yes.
Who's your ideal customer? Do you want to sell this to the everyman with the 3D printer, or do you aim for those big users?
So at this point in time, we're doing elephant hunting, using the colloquial term. And the reason for that is we want to show people that our software can be validated for their systems and that they can gain confidence in our software. Going forward in the future, our goal is to build up a cloud platform where anyone can upload their model, leverage all of the knowledge across all the different users of the cloud platform so that even without printing out a product, they'll have some idea about how to change their model to get a more accurate product at the end of the day. And this is something that I'm very passionate about because 3D printing is being used in high schools, in universities, makerspaces, what have you. And so it just seems to me to be a shame that those users have to go through a lot of design iterations and be continually frustrated with 3D printing. We want to cut that down significantly so that they have a positive experience with 3D printing.
So you're the Wikipedia of CAD designs.
We want to work towards that future. Exactly right. I like to call it the Netflix of 3D printing. Yeah.
Awesome.
I think there's a question here. Yeah.
Why do you think that the complex geometries are a lot harder to do? Is that more based on the scans, or is that more based on the algorithm? And yeah, is there a way that you think you could scale, or not scale, but get to those complex geometries?
So definitely the scanning of complex geometries is a significant hurdle in and of itself. And there's a reason for that. If you have a laser arm scanner like the FerroArm, and you're moving it around this shape to collect the point cloud data, you have to be sure to move it around in a very smooth and continuous fashion so as to avoid having multiple layers of points stacked on top of one another. That doesn't ensure an accurate representation of your printed product. So that in itself is an issue. The way that we bypass that issue as of right now is to have a desktop scanner that rotates in a uniform manner, and you don't necessarily have to introduce the subjective element of a human operator to collect that point cloud. If you could bypass that, then there could be an additional feature in terms of the machine learning algorithm, depending on the complexity of the geometry. These are all solid shapes. But if you had a complex geometry with cavities or interlocking parts, what have you, you have to find some way of accounting for those unique features in your machine learning algorithm. At this point in time, we have a way of accounting for cavities. The idea is that we do transfer learning, transferring knowledge about how shape deforms on the outer boundary so you could more easily understand how shape's going to deform on the inner boundary. But if you have a lot of intricate cavities inside of the product, or they're interlocking in some way, trying to capture that in the machine learning algorithm could potentially be difficult. So that could be another complication as well as we go to more and more complex designs in the future.
Have you considered creating this simulation in a completely virtual environment and it virtually 3D prints based on the machine settings so that you actually don't have to deal with scanning?
Right. So there exist physics-based software solutions that offer such a virtual environment, and what I can imagine is that the machine learning software that we're proposing can be integrated with that. The idea being that by using this physics-based simulator, you get some training data, we run our machine learning algorithm on that training data, and we could develop compensation plans much more rapidly than what people may typically be doing using existing software. So that is indeed something to be aware of. But I'd like to note one thing here, that there's still an advantage to actually 3D printing a product, because physics-based simulators can only go far. They can't capture all the new features that are being added to 3D printers. And for example, in the past, they had one laser in a machine, but now they're moving towards having 4 lasers in these laser-based additive manufacturing machines, such as what EOS and Renishaw are currently working on. In the past, they had to have pure metal powders. Now they're working with novel powder recycling methods built into the machine. And the physics-based simulators just can't capture all those new modifications to the hardware, all the new physics that are introduced by that new hardware development. So there's still some need for actually 3D printing a product so you can learn, even in these new settings, what's going on, and not necessarily rely on these physics-based simulators that have a limited scope of application.
If somebody were to start doing something in 3D printing, where would they even start? Like, what printer, what scanner, how do you
Right.
files?
It depends on the end use, you know. So I guess, again, other people in the audience could definitely answer this better than I can. But, you know, for rapid prototyping, polymers, resins, those kinds of things work well. For critical applications or when needed, metal-based types of 3D printers are important. In terms of the kind of work that we've done, what I would say is when you're trying to understand how best to 3D print a product, it's probably a good idea not to start with your own complex product, but try to build up to it by using some more primitive types of shapes. For example, it's got some kind of smooth dome shapes or maybe a little bit more complex rectangular prisms, because these kind of shapes contain a lot of information about specific types of geometric features. And by learning that type of information, you could then print out one copy of your shape and transfer all the knowledge from the previous shapes to your shape. So you don't have to print out multiple copies of this complex design, just one copy leveraging all the other past shapes to understand how best to improve its quality. So I would say maybe start simple, even with your scrap products, if they're simple, start with those, and then build up to the complex design that you may have at hand. But yeah, at the end of the day, different types of printers depend on the different types of applications of interest.
Do you know, are any of these companies doing like over-the-air software updates to address some of the inaccuracies? And if so, is that something that you would have, if you have a 3D printer and you do a software update that addresses it, then do you start over with this process to readdress the new inaccuracies or lesser inaccuracies?
Right. So, the 3D printing companies are always updating software, and furthermore, a lot of the 3D printing companies have recognized the merits of machine learning for their closed systems. So for example, Markforged, they have this software solution, Blacksmith, that uses machine learning in their closed system with their sensors that are built into the printhead. They collect the data, they run the software, and they understand how to modify future layers of the build process, accounting for what's been done in the past, to get an accurate product. And what we're saying is, you know, even if they update their software, there's still something to be said about using past data, past materials, and past processes so that you could still ensure that you get highly accurate products without having to start from scratch for that new updated software. But I know that they are updating their software, and even some companies are using machine learning for their closed systems.
So the sensor on the head that you were talking about, could that be a replacement for the scan?
Indeed. Yeah, it could be a replacement for the scan. The one thing about these closed systems that I'm not necessarily a big fan of is in terms of data sharing and kind of achieving a comprehensive platform for quality control across all different types of 3D printers, materials, and shapes. You know, it kind of reminds me, and I was talking to people about this earlier today, about how 30, 40 years ago, when it comes to computer software, you had, if you wanted to build a software package, you had to build a specific one for an Apple computer, you had to build a specific one for an IBM computer, so on and so forth, for all these different manufacturers of computer hardware. And to me, that just seems a shame, because machine learning is universal. It can be applied to all different types of printers, shapes, materials, and processes. So to restrict yourself and to live in this closed paradigm, I think it's kind of limiting the potential of 3D printing and limiting the potential of everyone to get involved with 3D printing going forward in the future.
Currently, you're using, you're sort of focusing on the geometric dimensional accuracy. Have you looked into thermal capabilities and modifying it in those regards?
Yep, that's definitely something. Yeah. We're very, very interested in that going forward. Again, right now we're just working with the bare minimum inputs to try to accommodate all the different types of machines and processes that we've been working on. But you're exactly right. The thermal history is very important. Getting some idea about tensile strength or other types of strength parameters for 3D printed products, that's also important as well. And yeah, that's something that we want to address going forward in the future.
Oh, it brings me in being curious as to what your roadmap is. So you're starting here, and then kind of where do you see maybe in the next year to 5 years out?
Right. So we're seeing within the next year, working with our current partners, validating our software for their systems. 5 years out, we want to have a fully working cloud platform that anyone can upload their designs, use our software, and understand how to improve their processes. And then going from there, considering other types of properties, other types of critical applications, and I think the future is unbounded. You know, we could predict, but it's kind of hard to see all the future paths for growth, all the future development that can occur. So. But we know, you know, thermal history, strength, those kinds of things, that's what we have to target after 5 years or so.
Do you ever consider open source with the software down the road in terms of kind of opening that up to other developers to maybe see other efficiencies? Obviously, you don't want to give up all your secrets, but is there potential in that?
Yeah, I think there is definitely potential for that, and I think that's critical because, again, unfortunately, there's this tendency for people in 3D printing to live in the old paradigm of adopting or trusting physics-based models that I think are very much limited. So if we make the software open source, or if we make the understanding of the algorithms open source so other engineers can understand them and appreciate them, I think that would do a lot to accelerate the growth and development of machine learning for 3D printing and bring in new players into the field. That would just move the entire domain going forward. So I think there is a need for that, indeed.
So do you see like a marketplace where there could be add-on modules or?
Yes, indeed. And you know, this is the wonderful thing about 3D printing. So maybe we have one type of architecture, one way of learning that neural network algorithm, but people develop new types of architecture that constitute new modules or new learning algorithms. Maybe not in using neural networks themselves, but some new type of machine learning algorithm that could be that could be an add-on to the software. So indeed, that'd be something that would be facilitated by having this cloud platform that we're envisioning going forward in the future.
Any more questions, guys? It's been very enlightening and just intriguing.
Thank you very much.
Yes, I do appreciate it. Good job. Very good.
Thank you. Thank you so much for giving me the opportunity to speak to you. I greatly appreciate it. Thank you.
Thank you. All right. Well, guys, there's still, I think, more beer left. Pizza's probably gone, but the beer is there.
And feel free to take a look at this if you like.
Yeah, we got a lot.